this is the example we will try to we will discuss, and we'll take some levels which may be appropriate for some region near lead 208 if you like, and we'll try to solve those equations. But so essentially the structure of the problem is one where the ingredients, if you remember in this Hamiltonian, is the constant G, which measures the strength of these correlations, and the single particle degree of freedom, which is the distance of the single particle energies. So contrary to the electron system, this energy distance here is not negligible with respect to G, and the competition between pairing and single particle becomes more interesting, and actually that will be the subject of most of the activity this afternoon. But what can you say even if you don't solve the VCS? So that's the distance, and this control parameter X, which is the constant of the strength, and if you remember the degeneracy, the gap was G omega, and then the other energy scale is the distance between level. This is some kind of control parameter that will drive the system from one limit to the other. So what happens if X is very small? Sorry? Exactly. See, if either the pairing strength or necessarily the distance between the levels is very large, that number is very small, and then, as he said, single particle dominate. And actually, this is so in nuclei to some extent, because there is a problem that you guys will solve, try to estimate what X is for nuclei, and that's why lead 208, for example, is still magic and is not washed out by pairing. And so when you solve the equation, and if you have, imagine that you have this set of levels, so you have a P3 half, etc., and you solve the single J. Pete show you how to solve that. So X very small. What is the structure of the pairing gap that you will see? And it's already shown here, so you don't have to go very far. But do you understand why would be? So essentially, if X is very small, you go through the shells, and every time you hit one of these levels, you hit a single shell. And you know how to solve that because Pete already told you. And so you see the little parabolic behavior of this single shell. It's maximum at mid shell with a maximum here, which is essentially omega over 2. And you see, for example, for the F7 half and so forth. So this is the way it looks, 7 half, 13 half, etc. Now, if G is very large, which means that essentially G is such large that this little d here doesn't play any role, then you are going to see essentially a big shell. All the shells are collapsed. That would be why, if you were to have a strong pairing interaction, nuclei will all look the same. They will look all sort of like this. Just a big shell. But in nature, actually, with this G of order 20 over 8, it looks sort of like in between, and you see still some effects that are left over, and we'll see that in the problem tomorrow. In the same way, you can look at the behavior of the Fermi energy, if you like. If you have a very small value, you feel the level, then you jump to the next one, then you feel the next one, etc. And it's a ragged, broken line. In the limit of strong pairing correlation, it's a big shell essentially, and you just feel it smoothly all the way through. In the middle is something which still may show effects of the shell, but is somewhat washed out from the sharp Fermi surface of the single particle picture. I gave you before some pairing gaps that people like Jensen's and Gregor Hansen's describe. In the VCS approach, you go a little step further, more microscopically, and you actually look at the values of the pairing strength. And it's not surprising, again, that the pairing strength depends on whether you have neutrons or protons, because of the potential changes with isospin, and therefore those are expressions that people have used to study by fitting pairing gaps in regions of the nuclear table. So there is a constant isospin dependent, about 20 MeV as we said before, but there is a correction due to the isospin in terms of N minus C. So we'll try this sometime tomorrow in the hands-on activity. Thursday. Okay. So we argue, or Molinari, Schiffer, and True argue that the two ingredients, the most important ingredients of the residual interaction were these two. And we discussed so far the pairing part. But then there was the other part, the quadruple. Now, at this point, let me stress that nuclei are more richer than these two ingredients. I think what these people tried to do at that time is to extract the main drivers. But you know, lead-208 is an octupole phonon. So there are also other terms in the interaction that will appear. So we are talking about the major ingredients, and of course the details still there, but this is the major framework, so-called pairing plus quadruple approach, if you like. So we look at the pairing, and for that approach, we argue, well, pairing the nuclei in a state of angular momentum zero is the one that actually becomes more efficient, and therefore the pair wave function is written. Now if I look at this one, now you realize that the P2, when I plot that as a function of the angle, has a range which is much larger than just 180 degrees. So in fact, if you have these orbits again, a la Schiffer-True, where you have these angles given by the plane of the orbit, you can estimate that the angle separation of these orbits actually goes like 1 over the square root of j. So the larger the j, the smaller the separation of these orbits. And if you have actually an interaction which sort of likes to be actually the P2 term has something of the order of 90 degrees if you look at the at the plot of the P2. Then if you can put them in such a way that the angles of this is smaller than 90 degrees, then you make a strong correlation, because they are close by, they still feel that. And it turns out, and maybe, I don't know if this was discussed by Rick or Mark, you can imagine the Align-Kapinski when you put all of them in orbits j minus j, j minus 1, etc., trying to put the particles in orbits that maximize that overlap. And if you were to have that interaction available to you, then you can convince yourself that now is not only the next pair that the next neighbor, but you can actually find out that the quadrupole force now goes like n squared times V2. So then the consequence is the following. You have the two terms, you have the pairing term and you have the quadrupole term. And now the two of those compete, and there is an exercise that will work this afternoon. You guys will have to solve it. If you were to have some conditions for which at some point when you start to add these valence particles n, there could be a place where n takes over. And although when n small you are dominated by this, at some point there is a change where the quadruple dominates. And you can show the condition, you have to solve that this afternoon, but essentially what happens is if you start to be dominated by the quadrupole, you start with a pairing coupling scheme, we have a 0 plus well depressed, but now the quadrupole starts to take over the 2 plus, which is the lowest excitation generated by the quadrupole force, comes down because it becomes extremely easy to generate that, and then you switch from the pairing coupling scheme to the aligned coupling scheme where you are dominated by this term compared to that. That doesn't mean that they don't coexist, because the scales are so similar in a way that you cannot talk about one without the other. So what does it mean? If you are near lead 208 or say tin 100 or tin 132, that's a good closed shell. But as soon as you move out a little bit, you will have quadrupole, and that's why the tin change, the 2 plus, is not as high as it should be, because the quadrupole lowers a little bit, but still it's a quasi-particle system. Now if you go now to the other extreme, you have many particles outside closed shell. The main role will be that of the rotational or essentially rotational state, which means the deformation takes on compared to the gap, but that doesn't mean there is no pairing by any means, as we'll show you later. Pairing still influence that because the scales are, and that's what it makes the nucleus very rich. All these three scales, so we have the single particle energy scale, we have the pairing strength G, and we have the quadrupole strength B2. So these three are similar, and it makes a rich, and I think I believe Rick and also Jean with the IBA already have shown you that rich that is, because that actually the IBA incorporates these ingredients in an algebraic form, which here we're trying to do with the hands-on, more sort of schematic way. So we'll work on that this afternoon. Now, I said that, so now you guys will tell me, then I go from tin 100 and I just add neutrons or protons for that matter, and then the system will come deformed. And well, that's something that already you learned is not true in the lectures before. So I had to be a little careful with that. This is just to show you, because of the dependence on the number of particles, you are actually going to be able to induce that transition. However, this matrix element there, this V2, actually is very strong for neutron proton and not as much for NN or PP. And the transition is driven by the neutron proton. We'll show you that a little later. So here, for example, I'll show you the case, one of the typical archetypes of these transitions, a real spectrum. This was sort of a cartoonish way, but you can see that indeed there is resemblance to data in the nuclear landscape. This is the case of the dysprosium nuclei. You start here with a nucleus that is dominated by quasi-particles and spherical systems. Then you see the 2 plus going down dramatically and changing from a sort of a spherical system to a rotor. And I'm sure that Rick have discussed that with you in detail. I'll remind you here a fingerprint for that transition, which was pointed out many times by Rick before, is that ratio which I show here as the 4:2. And you can see that's actually a very nice indicator of that something is happening. It goes from something which is of the order of, in the limit of pure pairing, where you have the 2 and the 4 degenerate, this value will be 1. And it goes from 1 to 3.3 for a perfect rotor. So now I can go back to nuclear data in Brookhaven and ask, can you plot me R4 to R2? And then you can make this nice plot, and beautiful actually. And now you see Augusto was lying to me, because you see I move in N or Z and the system doesn't really come deformed. It's only in between, because actually the main ingredient for that is the proton-neutron interaction. And of course, Rick and Ikuku Hamamoto early on pointed out that there is an empirical correlation of those properties with the number of protons and neutrons. So that n squared that I showed you before should be more properly considered as an NP-NN, and that drives the system from spherical to deformed. Of course, the correlations here of quadrupole type, they still remain, as we saw, for example, in the teens. Here there is a strong quadrupole correlation in the form of the phonon. Of course, this was discussed by Federman and Pittel when in their sort of unified description of the formation within the shell model. And again, it goes back to this strong overlap between spin-orbit partners of the neutron and proton, because as we argue, that geometrical overlap is maximized if the orbits are the same and they are on a t=0 state. They are very strong, and that makes that V2 in this simple picture very large, and it drives the system to be dominated by the quadrupole. So this cartoon you probably saw, I borrow it from Rick to actually show you in a pictorial way that in a vibrational region, you imagine the nucleus is like a sphere. You're dominated by pairing, and then the excursions of equilibrium are in the form of a vibrational nucleus. That can be associated with the potential in the terms of that the formation degree of freedom minimized at beta 0, and then some kind of a parabolic shape, and the energy is that of the vibrator, 2 plus, 4 plus, etc. Keep that in mind, because that's something we will try to also extend in the pairing form. Now you start adding the valence nucleons, and then at some point, as we said, because now the P2 terms, which goes like the n squared, starts to dominate, that changes this potential and starts to make some kind of excursion in this axis of deformation. It becomes flattened, and at some point it minimizes. So there is a transition from one, which is spherically, and Rick, you probably discussed the sort of a transitional.
Mark actually
mark this sort of the so-called X, X5 and E5 symmetry, which are
Mark or Jan?
on Norbert.
That's like Mark or Jan.
So Norbert discussed this sort of critical point phase transitions, notably in the shape degree of freedom E5 and X5, where the potential underlying the microscopic structure is somewhat flat before it goes from this to that. In this limit, the rotor energy that goes like II plus 1. So you see, the energy of the excitations of the system are strongly related to the underlying microscopic structure, and therefore that is an indicator. And we will use this later, of course, when we look at the pairing problem this afternoon. So, a rotor. You know that well. Quantum rotor expression II plus 1, and there is a moment of inertia. And so we said that even if you are dominated by the quadrupole, that doesn't mean that pairing is not there. And pairing actually manifests itself in the fact that if you were to calculate microscopically what is the moment of inertia of a set of nucleons moving in an harmonic oscillator, and you sum the contributions of the angular momentum of of each of those particles. Actually, this is called the Inglis formula, who developed that in terms of a perturbation theory. You find that it should be the rigid. That's very impressive, isn't it? I mean, just you have a nucleons in an harmonic oscillator, you sum that up and you get the rigid. Like if you have a microscopic football and you calculate, given the deformation, that moment of inertia, these guys should be the same. That's amazing. And then you go to experiment and you see, well, that's not what you find. Okay. So actually, and the reason is so beautiful and so simple, because now that we understand about pairing, and you see, you sum here the contributions of each single particle, you immediately realize, well, if these particles are actually going to be paired in spin 0, they cannot contribute much to this expression. And long and behold, now you do this expression, but now what do you use instead of single particle here? Yeah, we introduced the quasi-particles a few slides before. Now you know how to work that. You use the quasi-particle formalism, and you write the English equation, and then you come up here with two things. First of all, you remember the single particle energies are changed by energies which are actually now very large because they start with the gap. And this expression gets modified by this, which now has the gap on it. So this term goes down because this term goes up. And then not only that, you remember that because of the pairing correlations, these guys have only a very limited window where they actually can work because of the, oops, sorry. Yes, this is a problem with this guy here, sorry. Very sensitive device. There is the UV factors that we introduce. And therefore, in order for these guys to contribute, they have to be available, because otherwise the UV will give you 0 here. And there are some ways of estimating this. I already done that for you. But essentially, what it is that this is the level now. Actually, I believe Rick has told you about that single particles in the deformed system are not called single particles, they're called Nilsson levels.
No, that's tomorrow.
ooh, I'm predicting the future then. Rick will tell you tomorrow that these are Nielsen levels, which are labeled a little different than the J of a spherical, but they are related too. But for you, it doesn't matter, isn't it? I mean, it's just a bunch of levels. Now you know how to solve these because you know how to solve VCS. So it's just a question of using these labels. And then you plot the UVs and that product that I showed you before, and you see it's maximized at the Fermi surface. If the gap is larger, of course, that Fermi surface becomes more dilute, and then you take action far away from the Fermi. If the gap's small, it's only those that participate near the Fermi surface. So when you do that in quasi-particle picture, the moment of inertia gets changed, and then you get a nice expression which is called Migdal formula. And you see that Migdal formula is very simple actually. There is a rigid term, so essentially at some limit you would expect that the system will change to that. And now the control parameter again, x here. So if the control parameter is very small, which is you are not dominated by pairing, this should go to 1 and get the rigid body movement. Yeah.
So this approximation pops right out of that sum over quasi-particles we saw?
Yes, yes. In fact, maybe we can try to play with that in the hands-on activities if you like. So actually, one can, once you do that, of course, you have to do a realistic calculation, if you like, to do the individual levels and do it properly. But we can go a little step further and take some values that we know. And if I take what I know about sort of G omega, which we already, and then I'm going to assume that in the harmonic oscillator, actually, and I would imagine Rick will discuss that tomorrow. Some of these levels, maybe I'll anticipate something here. Sorry, Rick. I think I know what you don't you feel that I don't respect here, as I show in the slide early, but if epsilon is here and I start with a J, actually it fans out. The slope of this is given by the quadrupole moment of that particular substate. And actually, this distance here, or the separation, increases with epsilon, as you see, proportional, and it's proportional to that. So this is not very quantitative, but it's just qualitative for you. No. So D I will parameterize as the harmonic oscillator energy scale times epsilon, and then I will construct X and actually look at some of the data. So if I go to the nuclear data tables again, look at nuclei which are somewhat, I would say, quasi-rotational, if you like. Yes.
So a little bit confused about this epsilon parameter. To me, from this definition up here, it seems like it's what we're defining as our quanta that we're putting into our harmonic oscillator. But then we have fractional epsilon down here. So I guess I'm not understanding it.
So actually, this is not sorry. The epsilon there is not the number of quanta. Essentially, these are the two frequencies, because now when you have a deformed system, you can describe that as two harmonic oscillators. So this is your nice deformed system, and then you can associate one frequency on the axis 3, and then one, either 1 or 2, which is the same, and that will be 2. So the difference between those two is associated with the deformation. So the if you were to have epsilon 0, the two frequencies are the same as the frequency of the harmonic oscillator, which is spherical. The more you deviate from that, it makes this axis bigger compared to that, and that ratio or difference is related to the deformation. And you describe that in the Nielsen model by having two harmonic oscillators. That's the way Nielsen did it. You can have, in a more sophisticated way, an harmonic, a Woods-Saxon deform, and solve that. But in the Nielsen, which is I'm using here as harmonic oscillator, you will write it that way. And so, so then I go to the nuclear data tables and I look at rare earth, and yes.
So if you do this X is very small, then it is go kind of shell closure type construction, right? So can we verify this formula, this rigid, this moment of inertia there, because there the system will not behave as a rotor, it will behave as a vibrator, right? So how can we verify this model, because if X going to small, then this
Good point. Excellent point. Those with have a very sharp eye will see some yellow points here. Maybe not. You see yellow points here? That is the verification of those, and I'll tell you that in a second. Do you see it? It's not good. I just realized it's not very good, but there are a few. So, I'll get back to you in a second. So I plot here a two-dimensional plot, which is the moment of inertia which I derive from the 2 plus. So assuming that is a rotor formula, I know the 2 plus energy, so I can derive the constant in front of that, which is the moment of inertia. But I pick nuclei for which measurement, and that probably was discussed by Norbert perhaps in his lecture, or did you discuss measures of BOV2 and things like that? Yes, so from the BOV2 or the Q naught, I derive epsilon, the deformation. I plot this, and you see many letters there. This relates to many rare earth and actinides nuclei, for which there is both data on Q naught and J over J rigid. And then I compare with the rotational flow, and you see, well, it's smaller. The rotational will be if the nucleus was completely superfluid, but it's not, as you see, because we don't lie here. But we are not there either. So it means that pairing is strong, but it only affects those nucleons which are near the Fermi surface. So it's partially superfluid, if you like. It's superfluid in the surface. And actually, if I take Migdal's formula with my parametrization here of what X is, I can draw the blue that goes with the blue points, because those are the rare air regions. And you see here H omega 0 and G and omega depend on the A, as we argued before. So I take that on somewhat of an average. And then you look at here, that's the actinides, a little heavier. So then the black sort of shaded area goes very nicely through the point. So I think the Migdal formula does a good work in correlating the data with the assumption of pairing correlations in the way that we have discussed. Now, there was an interesting question there. How do you actually confirm that this formula gets to the rigid limit when I take X going to 0 and I have, as we argued before, a spherical system? So I cannot do it. But how can I make x also small? Actually, I can make x small with d if I make epsilon large. And actually, Rick will show you tomorrow in the harmonic oscillator.
Augusto,
Yeah.
if you draw it out that far somewhere, the video doesn't capture it.
Oh, okay. So if I actually draw, and maybe I'll grab a figure for this afternoon that we can look together again. You find that because you have many levels, you start with this in the harmonic oscillator. It turns out that for particular ratios of this omega 2 over omega 3, in particular a 2 to 1 ratio, which means the axis is 2 to 1, there is also a large stability at closed shells, because these guys sort of make this. I'll show you a real nice graph. So lead-208 here, for example, is a very closed shell spherical nucleus, but they, for example, dysprosium 152 is a fantastic super deformed nucleus for which the ratio is 2 to 1 and is deformed. But for that one, pairing again will be small, because now there is a large deformed gap, and therefore moment of inertia should approach, in this case, 1, which is what you just said. But we are in the other limit, and those are the yellow points, okay?
Could you show where the yellow points?
Sorry. The yellow points are derived there from some super deformed bands in dysprosium, mercury, and actually you probably have heard of shape isomers in the actinides too. Plutonium, uranium, they have a shape isomer, which is in the plot that that I show you from Rick. You have a potential energy as a function of beta, which sort of it looks like this. There is a minimum at about sort of 0.2, 0.3, and then it does sort of like this, but it's a second minimum, and this is a 0.6. Actually, 0.6 is equivalent to 2:1 ratio in the Nielsen model. And this is called shape isomer, because it's the same nucleus, the same isotope, but the only thing, and this is very, very different from this state, and therefore is very retarded. You cannot connect them very easily, and that's why it's called shape isomer. It lives long because it cannot talk easily to that one. And that one is also here. Now for those, the formation is large. X, say for example here there is a uranium point, and it's a uranium point there. This is the normal deformed, this is the shape isomer, very close to region. So I think this picture was very nice. Yes?
Sorry, I missed the point how your gray or blue surface are calculated.
So I take this and I calculate a range given the fact that in this region of masses I go from erbium 150 to 70 something. So I use the A's of those streams, if you like, and plot those limits from this formula. And the only variable in this formula is epsilon, because I know G, I know omega, and I know the parametrization of those with A.
So basically, the width of the surface
Is the mass region of the rare earth that I use, and for the black is the mass region of the actinides.
is this somehow related to the which shell you use close to the Fermi surface to
For-
calculate omega.
Yeah, correct. Now I can do the reverse, and that you will ask, of course, why don't you do that? Yes, I can actually do the reverse. And for assuming that Migdal formula is correct, because I believe pairing is the basic ingredient here, I can do the reverse and calculate the gap that I will require for these many nuclei in the nuclear table to describe the 2 plus. Okay, and I do that again. I know the nuclear data, I took all those, and that's what I find. Pair gaps from rotational moment of inertia. Okay? Completely different, observable, and it lies very close to those gaps that Bohr Mottelson derived from mass difference. Unbelievable. This is fantastic. You know, really tells you that there has to be pairing. There is no question about it, isn't it? Because, I mean, this is really two completely different two completely different observables. One is moment of inertia of the 2 plus. The other one is masses of the ground states are very nicely put into one single picture that is driven by the pairing. Now, of course, again, there are fluctuations and a structure there that makes nuclear very interesting in themselves, each of one, but the overall ingredient seems to be there as the pairing correlations. I think I find this very nice. Okay. Questions? Oh, because, yes, this is done, the way I do it is for isotopes. So I take just Z from, it's easy to grab that from ENSDEF. You get an isotopic change and you run it for those. Okay, so, yes.
Another question. In the previous slide, for example, for deformed bands that are constructed for two particle to hole excitation, you can find in the super deformed band of calcium or stuff like that. How this will be, because pairing should be important.
Yeah, well, in there, you can actually estimate what, if you were to use that in a Nielsen model, you can estimate what the RIGI will be and what you measure. And there you will find something that I will discuss a little later, which is called blocking. So related to that, and the analogy that Bohr Mottelson and Pines proposed in '58, it's not surprised that Mottelson and Vallotton say, well, I mean, this is superconductor. I know I break superconductivity with a magnetic field. So in nuclei, the analogy of magnetic field will be the angular momentum, because those will like to break the pair. At some point, I should quench superconductivity. So, well, how will that work? And that's easy to estimate. If you imagine a rotational nucleus for which there is no superconductivity, that's the red line. I squared, I mean, I'm assuming I squared, not I plus 1. Rigid moment of inertia, that's what we just say. But we just say pairing is there, so it cannot be that the picture. So actually for the nuclei in the ground state, I will start with the gain energy, which is the correlation energy, usually delta squared over D. So I'm below the what it will be the single particle ground state by the pairing correlation energy. But what is the price that I pay? Well, the price that I pay is the fact that the moment of inertia is not the rigid. Actually, if we go back to my plot over there, I would say, I don't know, maybe a third of the rigid. Take your pick, whatever you want, a third. And so it's simply, then I get I squared over 2, I rigid over 3. And then when you do that, you see that those parabolas cross at some point. What that does mean? Well, it means that at that point, I quench BCS. All the particles will break. I rather give up the energy in pairing and put it in the rotation, and that will be the pairing phase transition in nuclei as the Waterson-Balatan effect. And people got very excited because early results from Sweden, Arne Jonsson, show a discontinuity of the energy as a function of a band, as a function of angular momentum. They discovered the quenching of VCS in nuclei. But actually it turns out that that was not the case. And the reason for that,
Sir, I just missed the point. How we get this I divided by 3 term?
where I put, oh yeah, I put the 3 there because if I go back to this plot that I show here, I would say about a third, maybe a fourth, whatever. Something which is not the rigid and closer to a third. And I mean, even if you take half, it will move further out, but there will be a transition here into, depending on the nucleus, of course, as you saw, that depends on the actual nucleus you are in. But overall, I will expect a common feature that at some point Motteson and Balatan will take on. Now, the problem with this picture is that actually, as we say before, each single particle, each nucleus is its own identity, and some of these particular orbits are a little better than others in terms of Coriolis interaction. And that can be understood in a simple cartoon again. Here you have this pair of high J orbits, okay, say, or the J orbit. I'm not saying high J at the moment. I'm just saying I. And you see here that's this parabola I squared over 2J. However, if I'm going to break that pair and make an aligned orbit like that, which now generates angular momentum by summing those two, you can show in a very semi-classical way, if you like, that this parabola starts now at 0 at the low energy, but it has 2 times the aligned speed. And you can see that they will cross there again because it cost you 2 delta to make that, but it's huge, large amounts of angular momentum. So actually, pairing, if it were completely not selective, it will generate the phase transition. But because the structure of the single particle, some particles are better than others, let's say, and the so-called Stevens-Simons mechanism takes on. And what you see is an alignment of one pair. And that actually generates a discontinuity in the band, because you start like this and then you switch to that, and you can confuse that with the picture before, which will generate a similar behavior. But the physics is not the same. It is related, but it's not the same. It's so-called backbending mechanism, and the reason why is that is it'll become apparent in a minute. And essentially, it happens when this term, which is the Coriolis term, J dot I, divided by the moment of inertia, becomes something of the order of the 2 gap. So the first particle to align will be that one of a high J. The lower angular momentum will come later. Yes?
Can you explain why this quantity reflects the classical concept of Coriolis?
Oh, because the Coriolis force is essentially J. If you have a particle moving in a rotating frame, is J of the angular momentum of that with the angular momentum of the system. So the Coriolis force or the Coriolis interaction essentially is I dot J.
Augusto, I'm going to talk about that tomorrow. I don't think they've. Has anybody talked about Coriolis yet? So I'll
Okay,
discuss
so
it tomorrow.
very good. Please.
So if I understood it right from physical point, so the nucleus is spin, and then at some point the structure will change and it becomes something else in that phase.
Correct, correct. Which Mottelson and Valatam thought that it was just that if you had a superconductor and at some point you increase the magnetic field, they all ampere. Here, that will be the case. All the particles are paired, but suddenly at some point they start to break, all of them at the same time. Yeah, because when you have a gyroscope, if you like, a gyroscope, you know, they try to align with the angular momentum of the system. If you have a gyroscope in a little turntable and you start to spin, the gyroscope tends to align with that will be the classical way. This is quantum mechanics, but still it goes into a phase transition. But it's not actually. What happens is these particular orbits align. Now we will go further because, as you know, those others will align at some point. So actually, will you discuss the Crankinal picture? So this is more like an informative slide. It's not part of the lectures per se, but I thought because of the jargon of high spin physics requires some things that you may not be completely familiar, I thought of put it here as a dictionary. So essentially, you have, as I showed before, the information that we get is energy versus angular momentum. That's what we have. This is when you do gamma ray spectroscopy or particle spectroscopy, you have levels, excitation energy, and hopefully spin. So you have energy versus angular momentum. If you have those quantities, you can calculate a rotational frequency, which is related in classic Hamiltonian to the derivative of the energy with angular momentum. Now you do have the angular momentum because you measure that or determine that from experiment. So you have actually that angular momentum as a function of frequency. And if you have angular momentum as a function of frequency, then you have moments of inertia. There is the so-called kinematical moment of inertia. That's the ratio of spin over frequency. Very simple. But then you can have the derivative. That's called the dynamical moment of inertia. This is di d omega. Okay, so we look at data experimentally, and we usually give you a moment of inertia, I1, which is the kinematical moment of inertia, or I2, which is the dynamical moment of inertia. Now, those of you which are versed in classical mechanics will immediately realize the connection of these to mass. So in actually classical mechanics, you find you have the kinematical mass, which is the relation of P with V, but you can also have the dynamical mass, which is that response of the dp over dt, so essentially it's dp over dv. That's the second one. It's the one that goes into Newton's law. And that's the reason why we don't go to the third derivative, because we don't need it. All the dynamics is given by those two, okay? You know those two, you know everything. So, and now, having introduced that to you, then I can show you some nice plots here, okay? And then this is the energy versus psi. That's what we have in experiment, as I showed you before. You have that band there that was the ground state band and the aligned band. And now the real band depending on how those mix, will follow some kind of the orange pattern. And then if I plot angular momentum versus frequency, it will look like this. At the beginning, it will be a straight line, which follows the red. And then at some point it crosses to the blue, and that should be the same straight line but hitting at 10 because I have two aligned particles. So is the dynamic of a system that has two aligned particles and then rotates. So it should extrapolate back to this 10, and then it goes from one to the other like this, depending on how they mix. Now, if I now take the ratio of I versus omega, I get the moment of inertia I1, and you see that that is sort of like a constant here, which is the moment of inertia of this part. And then at some point it jumps, so it goes up because the spin increase, and then it goes down. So it comes constant, up, and then goes down. And then, of course, if I take the derivative, it's also constant, and then a big jump. And you see this quantity is very sensitive to signal a phase transition of some kind of a change. And that was the indication that people were looking for to actually see whether there was a BCS breakdown or not. If you make the interaction of the bands rather small, then you jump suddenly, and actually this plot backbends because you go from this curve and that's why it's called the backbending. If it is, the interaction is very, very large, then it's very smooth. So it looks more like this or even smoother depending on how the interaction of those two bands happen. Now, of course, this is a nice exercise, and of course, as I said, people show this experimentally, and this is shown here from that first plot. This was the band in dysprosium 160 as a function. They use h bar omega square here to make it a little better. You see, that's the rigid rotor value for that nucleus. The moment of inertia increases, and then suddenly a big jump. And approaching the rigid, everybody got excited. That's the quenching of superconductivity. But it turns out that that was not the case. And then you see many other nuclei here again, the sort of a backbending plot. This actually is the alignment plot. The I-13 have particles align very fast, and they give you this increase in moment of inertia compared to the ground state region where it's quenched due to pairing correlation. I think somebody already asked, and this is an example that came later actually from Berkeley. You see here as a function of frequency in the case of erbium, the first backbending, that's one particle aligns. But people, when they say, if it's really an alignment, that was Stevens, of course, and then they went up and did push the spectroscopy high, and then you see the second alignment. And the third, and should be more. And people now know that you go and align the lowest spin particles. And at some point, obviously, the question is when is, yes?
After the first alignment, why this band going down? Because with frequency that the moment of inertia going to be increased, and that should be.
This is, yeah, actually, that is a good question. I mean, you see here that actually the I2 or I1 that you plot, it goes up and then it goes down. At the region of the alignment that you gain a lot and then it comes back, it should come back to a value which is larger, which is the difference between this moment of inertia and that, and depending on what the moment of inertia is before or after, but the enhancement is at the crossing. Here, there is a large, and then you see it sort of comes back to a value that will be, but then suddenly another crossing comes online. So that means in the picture of band crossing that you saw there, you start you have one band here, then you have the other band there, then you other band, and so forth. And then you follow this sort of the envelope of those minimum. And at some point, you would expect that you will approach the rigid when all the pairing is quenched, and you expect that at some point that will happen. Now, of course, I mentioned the analogy to other fields, and the fact that you align those particles here, as I just argued, doesn't mean that there is no pairing. In fact, pairing still plays a strong role. This in solid state physics is called gapless superconductivity. So these particular orbits do not see a gap anymore, but the gap is there in the BCS, or pairing is still there. It's just that these particles do not see the gap anymore. That's why they call it gapless superconductivity. The system is still superconductor, but those particular particles, because of this strong Coriolis energy, they just don't see it, and they align. Okay, so
Really quenching kind of things, right? In quenching, all the pairs getting together.
at the same time, yeah, everything is just like in a real superconductor.
Just structure, but here it is not like that. If you go to higher angular momentum, then the second pair will be.
Correct. That's why, because, you know, in electrons they sort of all the same. Here, as I said, each nucleon in each orbit has its own identity, and therefore they are not sort of equal. Now,
How do you get this? I mean, you break two, so you break one pair, then you break or you, as you see here, you rather leave them carrying the shells. But I still don't get, why do you increase angular momentum, your energy drops?
oh, because the rotational energy goes with the rotational angular momentum. So in your Hamiltonian, is actually r squared over 2j plus the single particle energy, and this r now is I minus j. And if you have that one 0, then all is collective rotation. If you now split that r into the total and j, you gain 2j units of angular momentum that doesn't cost you any energy except breaking the pair. When that energy, that rotational part, becomes comparable to the gap, then you flip over, because it costs you less energy to align. That you can do with the gyroscope. Huh? If you spin very low, the gyroscope is running this way, it just keeps there. And at some point, the gyroscope, boom, aligns when the rotational Coriolis force compensates the loss in the internal energy. But what happens, of course, is the following. In the picture of that Nielsen model that you will see tomorrow, doesn't see very well. You see, this is yellow again. Yeah, there should be a yellow, sort of a yellow feeling here to indicate that this was sort of full, and sort of that's the Fermi energy somehow, and I have all the particles here. And imagine that they are all occupied, and then I have a pair of nucleons here. The pairing interaction scatters that pair into those levels which are above the Fermi surface, and therefore I can take part in that correlation. But now I just told you about the alignment. At some point, these particular 642 are the I13.5, as you will learn tomorrow from Rick. Then you align that pair. It means that you have to put one there and that there to give you the angular momentum. Now, when I occupy those orbits, you see I cannot scatter anymore to here, nor there, because of the Pauli principle. So now I'm blocking some of these levels, and my omega, which is not that omega, That's an omega that you will learn tomorrow. Is the projection on the symmetry axis blocks this orbit. So now my omega is smaller, which means that the pairing gap will go down because G omega goes down. And at some point, after I align many particles, I will not have any omega left, and pairing should go really to zero at some point. And we will expect that to happen at very high angular momentum after many particles have aligned. Now remember that this is a phase transition where that control parameter x, which was G omega over epsilon or delta epsilon or D, whatever, this is a phase transition. So at some point, if say in the ground state I am with an x which is larger than 1, and now by blocking I make omega, then at some point I will go from x larger than 1 to x smaller than 1. So pairing will be quenched, even if all of them are not aligned, okay? Because I made x smaller by changing the omega. So I could drive the phase transition. So maybe after the third or fourth back bending, if you like, the system will be quenched because x goes down and is below the critical value. Now, that means that is below the critical value doesn't mean that there is no pairing, and the relevant degree of freedom there is what we call pairing vibration, which is what we are going to discuss now, if we have time. Yes. Okay, so blocking, there was a question early on about these rotational bands which involve quasi-particles, excited quasi-particles, and that you can look by looking at multi-quasi-particle states which are formed in low excited isomeric states, which in this particular case are rotational because they form a rotational band in a high K component. And this is a plot from a review article by George Rakoulis, who sadly passed away not so long ago, who the group in Canberra look at this in very much detail. And they are plotting here the Migdal formula, which I just showed you before, and the J0, they call it Harris. That's an expansion that was derived by Harris. Essentially, that axis on the left is a fit of the experimental data by a Harris expansion. And then you see here, as a function of the number of aligned particles, this will be the ground state, and so forth, 2 quasi-particles, 4 quasi-particles, etc. And you see the moment of inertia, these masses are very similar. So the actual experimental data increases with the number of particles that you have aligned in the isomeric state, which is because of blocking. It quenches delta, and therefore it makes the moment of inertia larger, approaching the rigid moment of inertia, which actually is here in this line. And they find an empirical formula which relates the gap, say, when you have an aligned 2 quasi-particle state, appears to be 75% of that of the ground state. So this will be 2, ground state 0, so about 3/4 reduction. So then you can go and see, well, now we have 4 quasi-particles, that will be 0.75 or so forth. So at some point, the effective gap that you need to reproduce the moment of inertia is quenched, indicating that indeed at some point pairing is gone at high speed.
In
Yes.
this plot, I don't really
So here, I mean, as I said, I could have redone the plot, but essentially J0. So what they do in the Harris expansion is that they assume that the energy as a function of omega is some kind of energy plus 1/2 j omega square. And you feed this from the experimental data. So essentially it's an experimental measure of the moment of inertia. Usually in the cranking you use the Harris expansion because you do it in frequency rather than in angular momentum. So you have that, and then I go to my Migdal formula, the one that I showed you earlier, and determine the gap that I need to reproduce this. So when I have no aligned particle, here I know the structure, so I can calculate what the gap and so forth. So in order to reproduce this data, I need to put in the Migdal formula a gap that is reduced, and that is plausible because of what I said just before. Because of this blocking argument, I will expect that the gap when I have a one quasi-particle, an isomeric state here made out of those two particles, this blocks pairing is smaller and so forth. So this is an empirical way of assessing how much the pairing gets quenched as you add particles. And this is the way they parameterize that in the... Essentially what we expect is therefore, as in superconductivity, that at some point the gap with angular momentum or frequency will go down, and at some point it will be zero. Now, it never gets zero in the sense of it will still have dynamical pairing here. And that's what I'm going to discuss next. Because the fact that this BCS gap goes to zero doesn't mean that there is no pairing. It means that the nature of pairing or the dynamics of the pairing is in the form of a pairing phonon. That's coming up next. How are we doing?
10 and 12.
Yeah. So let me go back to that plot that we discussed early. This was introduced early on by Rick. So you have some kind of potential. You have a potential as a function, this degree of freedom, which is the geometrical deformation. You have a vibration, a potential like this. You change n or n and p, and you go into the form region, then you change from this to something that has a non-zero deformation, and the energy was an indicator of that transition. Now, we talk about pairing. Actually, we argue about this control parameter here, which is proportional to the omega g divided by d, and if this is large, then x is large, d, or you can go from, now I'm plotting a potential as a function of a deformation, but the deformation, of course, is not in real space in the sense that I'm not looking at the deformation of the surface of the nucleus. I'm looking at a deformation, if you like, of the pair field, if there is or no a gap solution. And actually, there is an analogy that you can follow, and then if it were a vibration system x less than 1, then you have something where the gap is sort of this alpha, which is the gap over G, is non-zero essentially. That will be a VCS solution. Here the potential is at 0, which means that there is no permanent deformation in the pairing's degree of freedom. at some point, if I change the control parameter, we argue that we will actually transition to a condition and where there is pairing. And that's something that will be part of our problem activities this afternoon, is to study this transition where you go from vibrations in this so-called gauge space to rotations in gauge space. And actually, there is an analogy that was, let me go there, discussed in detail by Broglia and others, but essentially between shape transitions and pairing transitions. The angular momentum, as we saw, was the key element that allows you to look at energy versus angular momentum and decide whether it was a vibration or a rotor. Here you imagine a real space. These are the Euler angles, and the system rotates in space and generates some kind of rotational band in physical space. Here, the equivalent of angular momentum is the particle number, and the orientation of the system is specified only by one Euler angle, if you like. There are no the Euler angles of the rotational system. Here is just one angle, and because the way that translates in a transformation that resembles a gauge transformation in particle physics, they call it gauge space. So actually imagine that this deformation is the deformation, if you like, of a Fermi surface, and if there is a pairing or no pairing, you can imagine your Fermi surface to be sharp or not, depending on whether, and if you have a pairing gap which is finite, then the Fermi surface is diffuse. If you have a pairing gap which is zero, the Fermi surface is sharp, but it vibrates collectively due to the changes in the pairing variable. Now let me go back, because I show you here these potentials, and does it really work that way in reality? And we have looked into that with my colleague at Berkeley, Rod Clark, and then you can see actually a simple result that shows you that potential as a function of this control parameter. And long and behold, when the parameter here is small, you see a parabolic thing. When the parameter is large, you see a minimum, which indicates that the pairing gap is non-zero. And in between, you see this sort of called critical phase point, which actually you discuss E5 and X5 with Norbert early on. I can tell you that this is called E2, because it's a pairing degree of freedom. So you can see that this is not just speculation, it comes up naturally in the system. Now, this violation of a spherical symmetry in physical space, Rick showed you, and I sort of reminded you today, that translates into a characteristic dependence of the energy of the system with angular momentum. And I will argue next that that should be the case here. For example, this is a more realistic calculation by Van Sorensen for lead 208. We know lead 208 is a very closed shell system, so you would expect an harmonic type of oscillator there, and indeed excursions of the gap centered at zero parabolic. But if you go to the TIN 120, which I gave you as an example of a nice pair system, indeed looks like a pairing gap around 1 MeV, as we saw in the figure before. So this the energy now, as we argue, is characteristic. We will pick up again this afternoon on this, but essentially if you are near lead 208, we talked about a phonon. And the characteristic of a phonon is a linear dependence of energy with the angular momentum, or in this case with the number of particles or pairs from the closed shell. And you see that the ground states of these systems do indeed follow a linear pattern, which is near lead 208. So proportional, and we will explore this afternoon. On the contrary, if you go to the tin region, this is again the tin from tin 100 to tin 132, and you plot the binding energy of the ground state, you find that indeed, actually this fit, which is shown there with the dashed line, is very close to a square approximation in the number of particles, which is the signature of the rotor. Instead of being I squared, the analogy is the number of particles, and that tells you exactly that, follows very nicely what you see in experiment. And the purpose of the activities this afternoon is to actually study this in the form of a single problem of 2 levels, which is easy to solve, and we will do that this afternoon in the activities. And to conclude, I think it's time for lunch, but I couldn't imagine a better way to give you another perspective of this, particularly with the excitement of the Higgs boson discovery and the Nobel Prize. This is a very nice paper from Max Planck Institute, and you can look at that. But essentially, let me show you the figure that they present there. And you see here, that's in superconductivity in traps. So essentially, you've been seeing the so-called Mexican hat potential of Higgs. And here you show the control parameter, which in this case is the current they apply to the superfluid system. And this is actually the fact that the Mexican hat deforms in non-zero deformation. That's the so-called Goldstone boson. That's the rotation in tin pairing rotation. This is exactly that picture. The system becomes deformed, and it actually generates rotational band. But this is the Higgs mode. So for those that were developed this constant, they were ahead of the time. The Higgs boson was the pairing vibration. It's the same mechanism, if you like. The difference, of course, is that we are in a finite system. But essentially here, they showed actually that Higgs mode in this paper, and this will be the pairing vibrations that we are studying in nuclei. So this is my last slide today. And so we'll get back this afternoon and try to understand a little bit better this system with some hands-on activities. And thank you very much.